Hello, everybody. Welcome to week 4 of HCDE's Research Seminar Series. So a special guest with us this week is actually near and dear to me because I get to introduce Aayushi Dangol. Aayushi Dangol is a PhD candidate in HCDE, and she works directly with me. I get the pleasure of being her PhD advisor as she's doing her research. So the work that you're going to see presented today is also work for my lab, so I'm excited about it. So Aayushi will be presenting on black boxes to playful inquiry, designing for children's AI literacy. And with that, I'll give it over to Aayushi.
Hello? Oh, perfect. Can you guys hear me? Perfect. Thank you, Julie, so much for the introduction. Hi, everyone. I'm Aayushi, and I'm really excited to be here today and share some of my work on designing for children's AI literacy. So when I was preparing slides for this talk, I asked generative AI to help me create an image of children playing with blocks. And this is what it gave me. This picture has one of the trademark flaws of generative image models. It doesn't know where to put the child's arms. However, unlike images, textual responses don't reveal errors in obvious ways. Instead, identifying mistakes like hallucinations in AI-generated text often require domain knowledge. And so, as a result, even trained professionals like lawyers can often miss AI hallucinations. For children, this challenge is even greater. AI-generated text often looks neat and convincing. Clear formatting, step-by-step explanations, citations, and dates, all of that can create an illusion of accuracy. And then there's the length. The sheer verbosity of some responses can increase cognitive load, making it harder for kids to spot inconsistencies or false claims. As a result, prior research has shown that children often overtrust generative AI, even when it's wrong. So as generative AI becomes more and more part of everyday life, there is a growing need to help children develop AI literacy. This includes supporting children in engaging effectively with AI, critically assessing its outputs, so helping children ask questions like, does this make sense? Could it be wrong? At the same time, we also want children to understand what AI is good at, where it falls short, and how that compares to what humans can do. However, this is challenging because many AI systems function as black boxes. Their lack of transparency makes it difficult for children to reason about how AI makes decisions or to know when and why its outputs should be trusted. So this raises an important question. How can we design and deploy AI systems that help children build AI literacy? That's the central question in my work. I use a mix of methods to address these questions. First, I use qualitative methods to examine how children, educators, and parents make sense of AI and where confusion emerges. I then co-design technologies with these same communities to understand what forms of support are most effective. And finally, I build AI literacy tools and evaluate them through deployments across classrooms, homes, and learning labs. Today, I'll be sharing the design journeys of 2 such AI literacy systems. First up is Clip4Kids. It is a child-centered AI system that invites children to play with how models classify and understand the world. With Clip4Kids, we wanted children to understand a fundamental process of AI decision-making, which is classification. This is where an AI sorts or labels data based on specific features. In our study, we broke this classification process down into three main parts. First, the classification rules. These define the categories the AI is trained to use. Second, the confidence score, which shows how certain the AI is about its decision. And finally, the decision threshold, which determines how confident the AI needs to be before it acts on that decision. In Clip for Kids, children explore these ideas step by step through three different interfaces. So they start with the word cloud interface, where a live webcam continuously captures images, and the AI's top 10 classifications appear as a moving word cloud on the screen. And here's an example of what that might look like. Next, they use the classifier interface. In this one, children make up to 3 labels for an image, like colorful bird, flying pet, green parrot. The AI then scores each label, showing how confident it is that the image belongs to that category. So for the green parrot image here, the model that we used says 97% green parrot, 3% colorful bird, and 0% flying pet. And finally, they reach the smart lock interface. This is where children decide what kinds of images should be let in through a virtual door. In this activity, children first determine the inclusion and exclusion categories for the AI smart lock. For example, they might choose humans as an inclusion category and aliens as an exclusion category. Then, they upload an image to the system and watch how the AI classifies it based on the categories they created. Children also get to experiment with the decision threshold, which controls how confident the AI needs to be before it unlocks the door. So for instance, if the threshold is set to 50%, the AI model will only open the door if it is at least 50% sure that the image belongs to the inclusion category. We designed Clip for Kids around 2 key learning considerations. The first was to help children compare how they classify information versus how an AI does it. Kids bring their own ways of thinking, shaped by their experiences and intuition. And when those clash with the AI's outputs, it might spark metacognitive reflection. So kids might ask questions such as, why did the AI think this? Or why do I see it differently than the AI model? The second design principle was encouraging iterative experimentation. In Clip for Kids, children can freely experiment with various image inputs and classification parameters. This allows children to refine their inputs, test hypotheses, and iteratively explore the relationship between their decisions and the AI's outcomes. The system also provides immediate feedback, enabling children to quickly observe the effects of their actions. We built Clip for Kids using the Clip Language Vision AI model. It is a classification model that provides visual capabilities for multimodal chatbots like GPT-4o and generative image models like Stable Diffusion. So to test Clip for Kids, we conducted multiple participatory design sessions with Kids Team UW. It is an intergenerational co-design group at our university. And so 7 kids between the ages of 7 and 12 joined us for a half-an-hour session for multiple weeks. For the sake of time, I will only talk about how children interacted with the smart lock interface. From our observations with children, 2 key themes emerged for our findings. First, children learned to understand and manipulate decision thresholds through hands-on experimentation. They were actively adjusting the AI's cutoffs and observing what would happen. Second, they began to question the AI's limitations, especially when faced with ambiguous or deceptive images. they noticed how easy it was to trick the AI. Let me share an example that really illustrates how kids engaged with the concept of decision threshold. In one group, we had Dylan, age 8, and Riley, age 12. And they decided that cats were allowed in, but shrimps were not. And so they uploaded an image of what they jokingly called a cat shrimp, a curled up cat that kind of looked like a shrimp. The AI classified it as 56% shrimp and 44% cat. And because the decision threshold was set to 30%, the door opened. Riley was surprised and immediately connected the outcome to the slider, saying it thinks that because of the slider. From there, Dylan and Riley began experimenting, trying thresholds at 20%, 50%, 70%, even 100%, noticing when the door opened or stayed shut. At one point, Riley even pointed to the score and said, "Everything from here causes the door to close," realizing it's not just about how confident the AI is, but whether that confidence crosses the threshold they had defined. Through this kind of iterative visual exploration, the children began to understand that AI decisions aren't static. They're shaped by adjustable parameters you can tweak. So far, I've shown examples of children exploring decision thresholds, but our second major finding focused on how children began probing the limits of AI's classification. In this example, Hannah and Nico, both ages 8, tried to trick the AI. They set dogs as the exclusion category and then uploaded a photo of a dog wearing a duck beak, essentially disguising the dog. Before testing, they predicted what might happen. Hannah pointed out that the image had dog-like features, fur, and a nose, but said that the beak might confuse the AI. And she was right. The AI classified it as 94% duck. Seeing AI's misclassification prompted Nico to reflect on the differences between human and AI decision-making. He said, "It's not the same thing as a human. AI thought that image was a duck because somebody put something like a beak." This playful but critical experiment shows how children were not only observing AI behavior, but also designing tests to challenge its decision-making. And finally, in the last group, we had a child named Alex, age 7, who explored how the AI handled classification rules using fictional Pokemon characters. As a Pokemon enthusiast, Alex set Charizard as the inclusion category and Pikachu as the exclusion category, playfully referring to Pikachu as evil. He did not like Pikachu. He first tested the system with standard images of both characters, and the AI correctly classified them, granting entry to Charizard and blocking Pikachu. But then, Alex posed a new question. What if we upload a picture of Pikachu dressed as Charizard? When Alex uploaded that image there, the AI classified as 73% Charizard, even though it was Pikachu in a costume, so the door opened. This moment illustrates how overlapping visual features can cause misclassification, particularly when the input blends characteristics from both categories. Alex grasped that the AI smart lock was responding to surface patterns that could easily be manipulated. Since conducting this study, we've implemented Clip4 Kids in other learning environments, including 5th grade classrooms at the University Child Development School. This work has also resulted in multiple publications, a few of which are linked here if you'd like to read them. Now, I know I've been talking a lot, and before I jump into what the second AI literacy system is, I'd love for us to try a puzzle. And I promise this puzzle is going to be highly relevant. So, okay. So to solve this puzzle, the first step is to look at the patterns here between before grids and after grids. And so what you should be able to find is a pattern that converts the before grid into the after grid. Would anybody like to tell me what the pattern is that's converting the before into the after? Yes, the borders, exactly. Can you tell me what's happening with the borders?
They are getting colored because of boxes.
Yes. So as you can see, in the before grid, it's empty, there's no color, right? But in each of those three examples, the border is being colored blue. And we can try that out. So here's our before grid, which is in different size than all these others. And so we can choose the color blue, and we can test the logic. So here we go. And we can submit the puzzle, and you were absolutely right. So now I'm going to move back to the presentation. Okay, so the puzzle that we just solved is an example from the abstraction and reasoning corpus, or ARC for short. It is a collection of puzzles that is used to benchmark AI reasoning. And this room was quiet, but we recognized that children actually really love solving these types of puzzles. And so because kids are drawn into solving challenges like this, we built an AI literacy system called AI Puzzlers. AI Puzzlers uses ARC puzzles to help children see what AI is good at and where it falls short. So in AI Puzzlers, children begin by solving one of the puzzles that I just demonstrated on their own. Then they ask an AI to solve the same puzzle and compare their solution to the AI's. And I'm going to show a quick demo of the different features that AI Puzzlers has. So, okay. So we solved this puzzle, right? And as you can see, there are different AI models you can choose from. So here we're using OpenAI's models. There's GPT 4.1 Nano, Mini, 4.0, 3.5 Turbo. And you can do a lot of things with it. And because we've already identified the solution for this one, let's ask AI a tricky puzzle, maybe like task 2, which looks different. So I'm going to choose GPT 4.1 Nano, and I'm going to ask AI to answer this. And really quickly, I'll also tell you what the solution is, which is in the after grid, what you see is this alteration of colors between the original color and the gray color. So if there is red and pink here, then in the after grid, the solution becomes red, gray, red, gray, red, gray, and pink, gray, pink, gray, pink. So that's our solution. And so this is the test that we want an AI model to serve. So when we click Ask AI to Answer, oops, sorry. Okay, so this was its answer. And so it's clearly wrong. Do you guys see how wrong it is? Yes. And then you can also ask AI to explain its reasoning. So why did you solve the puzzle this way? What pattern did you see? And so you can click Ask AI to Explain. And AI says, I looked at the old pictures and saw that some colors changed when they went through a pattern. So I replaced some of the white and green squares with gray, and I also changed some other colors like teal and red into gray and pink. So what we can see is it clearly does not know how to solve this reasoning puzzle. Now, We could do a few other things, which is we could give it directions on how to solve this puzzle and see if it captures the hints we give it. So what type of hint should we give the AI model, given this is its first solution? Anyone? Okay, I can come up with one. Yeah, we can try that. Okay, so it was alternate gray and color to the okay, going to the right. So this is our hint, and let's see how it does. Okay, a little better. Should we refine our hint one more time? Okay. Would anybody want to change it? Travis, do you want to change your hint?
Somebody else has better. On the same row.
Okay, yeah, on the same row. Okay, ask AI to answer. Oh, even worse. Okay, we can keep trying, but I'll move to the presentation now. But does everybody get an idea of how AI Puzzlers works? Okay, awesome. So we decided to use AI puzzlers to show children the reasoning limitations of generative AI for a couple of reasons. The first was that these ARC puzzles require no domain-specific knowledge, making them highly accessible. Second, AI models, as you just saw, routinely fail at them while humans excel. And finally, because these puzzles are visual, it's much easier to see when the AI messes up, unlike AI-generated text, where mistakes can be subtle or confusing. And so with that in mind, we wanted to answer two questions with this study. The first was, what specific limitations of generative AI do children recognize through their engagement with AI puzzlers? And the second was, how does presenting information across visual and textual modalities influence children's ability to critically assess AI-generated outputs? To answer these research questions, we conducted 2 co-design sessions with Kids Team UW, and 21 children between the ages of 6 and 11 joined us. We recorded their group interactions via Zoom and analyzed the data using thematic analysis. So I'm going to show a short clip, about 3 minutes, of children interacting with AI puzzlers. Okay. Hello? Okay. So I want to highlight a couple of things from this video. First, children had high expectations that AI could solve the puzzles. This belief in AI stemmed from their own ease in solving the puzzles and also their general trust in AI's broad knowledge. Second, the visual nature of the puzzles made it super easy to detect AI's mistakes. We had children who couldn't read, but they were able to solve the puzzles and identify that AI made a mistake. And lastly, seeing AI fail probed curiosity into why this would have happened in the first place. These moments sparked critical conversations about the strengths and limitations of generative AI, as well as the strengths of human reasoning. For example, children often described generative AI as having a scientific brain, good at memorization and data retrieval. Noah, an 11-year-old girl, said, "It's trying to solve it based only on the internet, but the human brain is creative. AI only has the info it's given, but humans have other experiences." A second finding that I want to highlight is that even as the puzzles got more difficult and kids saw that AI was struggling again and again, they kept engaging with AI puzzlers. For example, here's one of our hardest puzzles that a group of children successfully solved together. And here's what AI came up with. So A is children's solution, and B is AI's solution. And we found that this sustained engagement came from two reasons. First, they were genuinely curious. They wanted to see how the AI would mess up next. There was almost a sense of suspense, like, what weird guess will AI make next? And then, just as importantly, their engagement wasn't only just about AI. The puzzles themselves were a big draw. Kids saw them as opportunities to problem solve, to figure something out on their own, and that sense of personal accomplishment really mattered. Additionally, children's engagement didn't stop at solving the puzzles or watching the AI fail. They also actively tried to help it by iteratively debugging AI's errors. For example, children would often spot what the AI got wrong, give it a hint, test out that hint, and then tweak their instructions based on the AI's responses. So in this example, from 1 to 4, we see how detailed children's hints get and the corresponding solutions from AI for the hints. I want to share 3 design implications for child-AI interaction that emerged from this work. First, there's an opportunity to make AI reasoning more interpretable. Visual reasoning traces like flowcharts or decision trees can help children follow the AI's thinking step by step. Combining textual explanations with visuals can also reduce cognitive overload when evaluating AI-generated outputs. Second, confidence levels or uncertainty flags can help guide children's attention and support critical thinking. These kinds of validity markers might encourage kids to pause, question, or test what the AI says. And third, we need to design for experimentation and reflection. When children can adjust inputs or try different strategies and reflect on how the AI responds, it creates opportunities for interrogating AI's reasoning and making sense of its decision-making patterns. So what's next? I have been working on a system called EcoPrompt right now. It currently builds on everything I've learned so far from designing for children's AI literacy, but it adds a new layer, helping children understand the environmental impact of generative AI. When we use generative AI, it can feel free. You type a prompt, press enter, and an image or a paragraph appears instantly. There is no visible cost, no money changing hands. But behind the scenes, every prompt travels through massive data centers that consume huge amounts of energy and water to power and cool the models that makes generative AI possible. So the goal with the eco prompt is to make that invisible impact visible. When children interact with a chatbot or image generator, eco prompt shows how much energy or water might be used behind the scenes, or how that compares to familiar things like running a dishwasher. I'm currently testing EcoPrompt in classrooms and after-school programs to see how children reason about these trade-offs. And what I'm particularly interested in is understanding whether making AI's environmental impact visible changes how children use AI. Do they prompt less? Do they reflect more? Do they begin to see their digital actions as part of a bigger ecosystem? And my hope is that EcoPrompt will help children see AI as part of a shared material world we all depend on. And with that, this concludes my talk. Thank you so much for listening to me, and I can take questions.